Good afternoon. Today's topic is Maxwell's equations. And let's sort of catch up with where we left off last time, and we're going to make a small modification. So, first of all, back in chapter 23, we studied Gauss's law for electrostatics, and that's just the integral of E over an area is equal to the charge enclosed by that area divided by epsilon naught. A similar kind of equation is for magnetic fields. Since there are no isolated magnetic charges, B dot dA is 0 because you don't get magnetic monopoles. All the lines of flux that go in also come out, and so the net flux is 0. Faraday's law states in so many words, in a number of ways, we can create electric fields by changes in magnetic flux or magnetic fields. Ampere's law talks about the fact that magnetic fields are caused by currents. Now, if you notice, there's kind of an asymmetry here, where you have a symmetry between Gauss's law for electrostatics and magnetism. Faraday's law and Ampere's law seem to lack a symmetry, and that is the following. If changing magnetic fields can produce electric fields, Maxwell reasoned that, well, it should be that changing electric fields should also cause magnetic fields. So there should be another term in Maxwell and Ampere's law, and we're going to talk about where that term comes from and how we can make the case that indeed this term will represent changing magnetic fields, changing electric fields or electric fluxes causing magnetic fields as well as currents. So let's talk about that. We can say that the line integral over any closed path is over any path that a conduction current, a regular current, passes. And we define the conduction current, I, as just the time rate of change of charge carriers that pass through. And this is the usual manner that we think of a current. But this only works for electric fields that are constant in time. What we want to do is modify Ampere's law for a case where electric fields are changing in time. And here's how we might do it. Let's picture the following. Let's picture a circular capacitor. Wires going in and out of that circular capacitor. We have a current going in, I, of course, with the same current coming out. But of course, there's no current between the plates, at least as we understand it. So in this case, we have a positive plate here, we have a negative plate here, and we don't expect that there's any conduction current in the gap between the plates. Let's look at this a little bit more closely. Let's draw two surfaces, and let's have them bound by the same path. So I'm going to draw the boundary of the surfaces here. One is just going to be a circle around this path. I'm going to call that surface 1. The other is going to be a path that goes like this, in between the plates of the capacitor. I'm going to call that surface 2. So both surfaces are bound by the same circular path. Let's see what happens. Ampere's law states that B dot ds around the path must equal mu naught I, where I is the total current that goes through any surface bounded by the path. So, when this path is the boundary for surface S1, notice what happens. Integral B dot ds is simply equal to mu naught I, because I have conduction current passing through the path in that way. Okay, fair enough. But notice what happens when I have it pass through surface 2. In that case, so this is for surface 1, but for surface 2, B dot ds is equal to 0. There is no current in coming out of that path because I've got no current in between, at least no conduction current in between the plates. So we have a contradiction in terms. There seems to be some sort of discontinuity in the current. Well, Maxwell postulates that maybe there's some current, some other type of current that exists between the plates, and he calls that a displacement current. And that current would be proportional in his mind to a change in electric flux between the plates. And it would look like this, where epsilon naught is the familiar permittivity constant in free space, and this is the time rate of change of the electric flux. In other words, if I could add this term to Ampere's law, that would illustrate that changing electric fields or electric fluxes cause magnetic fields. So this would be two for the price of one. I would make my Faraday's law and Ampere's law symmetric, and I would have an explanation for why I have this apparent discontinuity in current between surface 1 and surface 2. And so that's what we're going to do. We're going to say that the capacitor is being charged, and while the capacitor is being charged, the changing electric field between the plates is considered equivalent to a current, a displacement current as it's called, that acts to make a continuation of the conduction current that comes in and goes out from the capacitor. So we have a nice continuous stream of current. Conduction current, then we have displacement current between the plates, and then more conduction current as it leaves the capacitor. Another way to look at this, notice that the electric flux through the surface, I can write E dot dA is my electric flux. And that's going to be equal, in this case, very simply, E times the area of the plates. And if we know that Q is the charge on the plates at any instant, we can write the following expression. We can say that E is equal to Q divided by epsilon naught times A, which I can write. In that case, I can say then that my displacement current could be written as epsilon naught times dphi dt, which would be the same thing as dq dt between the plates. So the displacement current is exactly equal to the conduction current in the wires. This is also equal to the conduction current in the wires. Therefore, it truly is a continuous form of current. I go from conduction current to displacement current and back to conduction current, but they have the same exact value. Beautiful. So two things have happened. We've explained how we can have a complete circuit even with space between a capacitor, and of course we've explained how we can make Maxwell's equations more symmetrical in terms of Faraday's law and Ampere's law. So it's very, very nice. So we can add to Maxwell's equation the displacement current term, epsilon naught, dphi electric dt. Let's do a couple of examples of this. Let's look at, suppose I have the following situation. Suppose I have an alternating voltage, a sinusoidally varying voltage, where the frequency of the voltage is 3,000 hertz. The maximum voltage is 30 volts. And I have a capacitor that has a value of 8 microfarads. And the question is, can we find the displacement current in the capacitor? Well, as a solution, we know omega then is 2 pi times the frequency, and that's going to be equal to 1.88 times 10 to the fourth radians per second. The voltage across the capacitor I can write as delta V max times the sine of omega t at any time, which is 30 times the sine of 1.88 times 10 to the fourth times t. My displacement current is just going to be equal to dq dt, which I can write as the time derivative of c delta v c delta t. I should say just delta v is equal to c times d delta v across the capacitor dt, which I can write then as 8 times 10 to the minus 6 farads times 1.88 times, times the cosine of 1.88 times 10 to the fourth times t. And that's my displacement current for this particular capacitor in an AC circuit. I'll do one other example. Suppose I have a case of circular capacitor. Suppose I have plates of radius r, and we're charging it up. Let's derive an expression for the induced magnetic field as a result of this charging up. Now, there's no current between the plates right now, so B dot ds then would simply be due to the changing electric flux. Let's look for r, little r less than capital R at first. That being the case, I'm only encompassing area of pi little r squared. And so this becomes b times 2 pi little r is mu naught epsilon naught times the time derivative of pi r squared times the electric field, which I can write as mu naught epsilon naught pi r squared dE dt. So that would be my magnetic field that's induced for a case where r is less than the radius of the plates. Let's look at the case for when I'm outside, when little r is greater than big R. So I'm out here. I'll put little r out here. That being the case, b times 2 pi r is going to be equal to mu naught epsilon naught times the time derivative of the electric flux, which is pi big R squared times E, which means I can put that all together and I get mu naught epsilon naught capital R squared over 2 little r dE dt. So my induced magnetic field, this is for r greater than r, and this is for r less than r inside. So we have a nice illustration, a second illustration of displacement current and changing electric field causing magnetic fields. That is the modification that Maxwell made to Ampere's law, which made the equations nice and symmetric. What I'd like to do is we're going to pick up with a couple of mathematical tricks and do Maxwell's equations in a different form next time, and then talk about the consequences of Maxwell's equations.